Picture a physicist at the very end of the 1800s, closing up the office for the night, quietly certain the great work is nearly done. 2 centuries of it. The motion of everything that moves, pinned down. Light, electricity, magnetism, pinned down. All that's left, the mood said, is tidying. Measure a few last numbers to one more decimal place and hand the finished machine to the next generation as a solved problem.
That mood was real and worth sitting in before we wreck it. Because we're about to wreck it thoroughly. You've spent a whole course on the clock, the motion of things, the wound-up machine that grinds the present into every tomorrow. And you're part-way through a second on the field. Light and electricity, the smooth, invisible thing that fills the room and carries the crackle and the glow. 2 triumphs. Tonight, both crack.
And from where I'm sitting, that confidence sounds earned, not smug. The clock predicted where planets would be years ahead, right down to the minute, and they showed up on schedule. The field predicted that light is a ripple travelling at one fixed speed, and reality agreed to the decimal. Honestly, if I'd been alive then, I'd have believed the tidying story too. So where does it start to come apart?
In the most humble places you can imagine. That's the first surprise. Not in some exotic corner of the cosmos, not out among the stars. It's a fireplace, a sheet of metal, a single atom. The most ordinary objects in the world, the sort of thing sitting in your own home right now.
3 humble little things then. A fire, a bit of metal, 1 atom. That's the whole case for the prosecution.
That's the whole case, and it's plenty. 3 humble little things, each posing a question a curious child might ask at the dinner table. And the triumphant Clockwork and Field picture, the crown jewel of 200 years, steps up to answer all 3, and gets all 3 not slightly wrong, but catastrophically, impossibly wrong.
Give me the flavour of catastrophically before we dig in, because I want to feel the size of it. Slightly wrong, I understand. The theory says one thing, the measurement says nearly the same, you nudge a decimal. Catastrophically wrong sounds like a completely different animal.
A completely different animal. Slightly wrong is your theory says 10, and the truth turns out to be 11. Catastrophically wrong is your theory says the answer is endless, without any limit at all. And the plain truth is, you're sitting comfortably by your fireplace, warm and unharmed, not being incinerated where you sit. That's the first crack, and it really is that violent.
Okay, not being incinerated is a bar I'd very much like our best physics to clear. So let's start right there. What's the setup? What is this humble little experiment that supposedly ends with me on fire in my own living room?
The humblest going. Heat something up and watch it glow. That is the entire experiment. Take an iron poker and push it into the coals of a fire. You've watched this 100 times. Everyone has, long before there was any such thing as physics. What does the poker do, colour by colour, as it heats up?
It changes colour. It starts dull and dark, then comes up to a deep glowing red, then a brighter orange, and hotter than a home fire can manage, I'm told it climbs toward a blinding yellow-white. The colour marches steadily up as the heat marches up. Redder when it's cooler, whiter when it's truly fierce.
The colour marches up with the heat. Hold on to that, it's the whole clue. And notice a second thing. It doesn't matter what the poker's made of. Iron, coal, a ceramic tile, the filament in a bulb. Heat any of them to the same temperature and the glow comes out the same colour. The colour is a thermometer. It reads the heat and almost nothing else.
That's a lovely fact on its own. The glow forgets what the thing is made of and only remembers how hot it is. So, the challenge to your confident end-of-century physicist is, what? Explain the colour. Explain why hot comes out red and hotter comes out white. That still doesn't sound career-ending to me.
Explain the whole spread of colours, really. A glowing thing pours out a whole mixture at once. Some red, some orange, some yellow, and a great deal you can't see. Off past the red, landing on your skin as warmth. Off past the violet, where your eye misses it. And experimenters had measured that spread beautifully. A precise curve, how much light comes out at each color.
And measured beautifully is about to collide with impossible to explain. I can feel the setup. But before you spring it, let me be sure I understand those two invisible ends. Off past the red is warmth I feel on my skin, and off past the violet is… what, exactly? Just more colors my eye happens to miss.
More colors your eye misses. But keep your attention fixed on that end, because that's where the trouble lives. Past violet, the ripples of light get shorter and shorter, packed tighter, and the light gets more energetic every rung. Violet, then the ultraviolet that burns you at the beach, then the X-rays a hospital uses to photograph your bones. Short ripple, high pitch, more punch. Long ripple, low pitch, gentle and mild.
Short ripple, high pitch, more punch. That's my ladder, I've fixed it in my head. Long and lazy down one end, short and vicious up the other. So now spring the trap. Your physicist rolls up his sleeves, sits down with the clock and the field, and sets out to derive that measured curve. What happens when he tries?
First, he pictures the glowing stuff the way the field course taught him. Inside any warm object are countless tiny electric charges, the bits that jiggle when a thing gets hot. And the field was firm. A jiggling charge sheds light, radiates. So a warm object is a vast crowd of tiny jigglers, each shaking at its own pitch, each pouring out light. To get the curve, you add up the light from every one.
Adding up a crowd. Fine, that's the sort of grind the clock is built for. Lots of little contributions, sum them together, out the far end comes an answer. So where's the danger hiding? Adding up a great many small things sounds tedious to me, but tedious and catastrophic aren't usually the same word.
The danger's hiding in how the total gets shared out. Classical physics had a rule it trusted down to the bone, a fairness rule. Once everything's settled at one temperature, every possible way of jiggling gets, on average, the same equal share of the energy. Perfectly democratic. Every pitch the object can ring at draws the same ration from the common pot. And that rule had worked everywhere anyone tested it.
And that does sound reasonable. Fair's fair. Every way of wiggling gets an equal slice of the pie. I still can't see the bomb hiding in it. Where does equal shares for everyone turn into your fireplace is now a death ray? Walk me right up to it.
The bomb's buried in counting the ways. How many ways are there to jiggle slowly, at a low pitch, in a long, lazy ripple? Not many. A long ripple is a big, clumsy thing, and only a handful fit inside the object at all, the way a plucked string sounds only a few low notes. Now the opposite question. How many ways to jiggle fast, at a high pitch, in a short ripple?
More of them, I'd guess. The short ripples are small, so you can tuck a lot of them in, pack them every which way. And I'd bet the higher you go, the more ways there are, since they only get smaller.
Enormously more, and you've spotted the fatal part. The count keeps climbing. The higher the pitch, the more and more ways there are, with no ceiling anywhere to stop it. And now marry that runaway count to the fairness rule you liked. Every one of those endless high-pitch ways stands there demanding its own full, equal slice of the energy.
Ah, and there's no top to the count. So more and more ways to wiggle the higher up the ladder I climb, each holding out its hand for an equal share, and no ceiling on how many hands there are. So when I finally go to add them all up…
You're adding an ever-swelling crowd of slices, each the same size, marching toward the high-pitched end with nothing to stop the count. And the grand total runs clean away to infinity. The theory says a warm object should pour out endless energy at the short ripple, high-pitch end, the ultraviolet end and beyond. Not a large amount, not a worrying amount, a literally unlimited amount.
Wait, infinite. Not a fair bit more than we measured, literally without any limit at all. Spell out what that means for my real living room, because I've sat by a great many radiators and never once felt infinite anything come pouring out of one.
Here's what it means, taken dead at its word. That warm poker, your cozy fireplace, the mug of tea on your desk. Every warm thing in the room should be dumping most of its energy at the highest pitches it can reach. The pleasant visible glow should be the merest afterthought. Your fireplace ought to be blasting you with ultraviolet, then X-rays, then worse. Warming your hands should cook you where you sit.
So my cozy little fireplace should, according to 2 centuries of triumphant physics, be roasting me alive with X-rays. Lighting a candle is technically attempted murder. My campfire is a death ray.
You really don't. And the physicists of the day felt every bit of the horror. It even earned a name that tells you how they felt. The ultraviolet catastrophe. Catastrophe, written down in dead earnest in a serious physics paper. Because the arithmetic was spotless, every step of it was a rule they trusted with their lives. And the answer it marched them straight to wasn't merely wrong, it was deranged.
An infinity, sitting there on the page, where the actual world plainly has something cozy and warm and perfectly finite. The maths and the hearth pointing in completely different directions.
An infinity where the world has a warm hearth. So look at what the real, measured curve does instead. It rises gently from the low end, swells to a rounded peak at some middling colour, and then, at the high-pitch end, curls politely back down toward nothing. It doesn't run away anywhere. It behaves itself.
So reality does the precise opposite of the disaster. The theory bolts off screaming to infinity, up at the high, short, punchy end. The real curve quietly settles back to 0 in that very same place. So they don't merely disagree on a number. Up at the top, they head off in flatly opposite directions. Something's gone structurally wrong.
Flatly opposite directions. And that's the real trouble, far more than any wrong number. It's not that the answer came out a little off, it's that every step looked utterly bulletproof, each one a rule nobody dreamed of doubting, and the whole thing still detonated in their hands. Something in that clean, trusted arithmetic has to be a liar, and the only question left standing is, which piece?
So who's the poor soul who has to walk into that mess and figure out which one of the trusted pieces is secretly the liar? Because I'm sensing this is the moment a name finally comes into the story.
This is the moment, and the man is nearly the last person on earth who wanted the job. Planck. Cautious, conservative, respectful of the old physics, the sort thrilled to tidy the last decimals. He worried at that runaway curve for ages, hunting for any trick that would bend it down to the measurements. He found one, and he loathed it so badly he called it an act of desperation.
An act of desperation. What a magnificently grim phrase from a man who's quietly solved the biggest problem in all of physics. Most people would take a slow, deep bow and enjoy the applause. So what on earth was this desperate trick? What did he have to force himself to swallow to stop my fireplace from murdering me?
He had to assume energy does not come in a smooth, pourable stream. When one of those tiny jigglers gives up light, it cannot hand over any amount it fancies. A dribble, a sliver. It can only pay in whole lumps. There is a smallest coin. You can hand over 1 lump, or 2, or 3, but never a lump and a half. Energy at the bottom of things comes in indivisible grains.
Lumps instead of a smooth stream. All right, I'm with you that far, but I still don't see how that stops the infinity. Coins or a smooth pour, if there are endlessly many creditors lined up out the door demanding their equal share, I still go bankrupt at the end of the day. What does the lumpiness change about that runaway count?
Everything. Because of one more thing Planck had to say about the lumps, and this is where the rescue lives. The size of the smallest lump is not the same at every pitch. For a low, lazy ripple, it's tiny, cheap, easily afforded. But the higher the pitch, the bigger the smallest lump you're forced to pay in. High pitch, expensive coin. The shortest ripples can only be bought in enormous lumps.
Oh, that's clever. Let me say it straight back to you. For the low pitches, the coins are loose change, easy to fish out and hand over, so those wiggles light right up. But for the high pitches, the exact ones causing the whole run away to infinity, the smallest coin you're allowed to pay in is huge, which means
the warm object cannot afford it. Temperature is a budget. A warm thing has only so much energy to hand around in modest amounts. At a low pitch, the coin's smaller than that, so it gets paid over and over. At a high pitch, the coin costs far more than the budget usually has, so nearly always it doesn't get paid at all. That wiggle stays dark.
So the high-pitch wiggles don't get their equal slice after all. The whole fairness rule quietly breaks. It swore blind everybody draws the same ration. But if the ration only comes in coins, and the high-pitch coin costs more than the object can scrape together, then the high-pitch wiggles go home empty-handed nearly every time. The runaway crowd gets priced clean out of the room.
The lumpiness is a tax that falls hardest on the highest pitches, strangling the runaway right where it was running away. Add it up now, and the curve rises, peaks, and falls to nothing at the high end. The measured shape, dead on. No infinity, no death ray. A warm fire that warms you and does not cook you.
And it explains the poker beautifully too, doesn't it? Let me check it out loud, slowly. A cool poker has only a small budget, so it affords nothing but the cheap, low-pitch coins, the red ones. Then you heat it, the budget swells, and now it affords the pricier coins up the ladder. Orange, then yellow, so the glow climbs toward white. The colour was the size of the budget the entire time.
Exactly. And that's how strange this fix is, underneath how well it works. Nothing in the clock, nothing in the field, ever said energy ought to come in coins. A ripple is smooth. That's its whole nature. Planck put the graininess in by hand.
Purely because it worked, for no better reason than that it happened to produce the right curve.
Purely because it was the one thing in the world that bent the curve onto the data. He had no reason for it beyond that. No deeper picture, no mechanism, no story. Assume grains and the numbers come out right. A patch wearing the clothes of a law.
And he never made his peace with it, I'm guessing. A man who calls his own crowning triumph desperation doesn't sound like someone who slept soundly for the rest of his life.
He couldn't stand it. He spent years trying to unsay it, hunting for some way to let the smoothness back in and demote the lumps to a bookkeeping trick, not something truly out there. He never managed it. The lump was real, the first grain of a graininess hiding everywhere. But he went to his grave uneasy about the door he'd opened.
But one strange fix, squeezed out of one strange experiment, is a curiosity, not a revolution. I'd want a second witness, a completely separate one, before I'd believe the whole world is secretly grainy. Otherwise it's Planck's odd trick for hot pokers, and I get on with my day.
You'd be right to hold out for one, and ideally a second witness you don't have to take on faith, because the fire asked you to picture an invisible crowd of jigglers you'll never actually see. The second witness is about as concrete as physics ever gets. You could very nearly run it on a kitchen bench with things you can hold in your hand.
Concrete is exactly what I want, after all those invisible jigglers I had to take on trust. So hand it to me. What's the experiment, and what am I actually looking at this time?
Take a clean plate of metal and shine a light on it. Under the right sort of light, the metal starts throwing off tiny electric charges. Little bits, electrons, kicked clean out of the surface and up into the air. Light goes in one side, sparks of charge come flying off the other. That's the whole experiment, top to bottom. Light knocks pieces loose from a piece of metal.
All right, that one I can picture with no faith required. Light hits the metal spits out little charged pieces. And through the field course's eyes, that even seems reasonable. Light is a wave. A wave carries energy. The energy pounds on the surface until a loose piece shakes free, like sea waves working a pebble out of a sandbank. So, where's the trouble this time?
The trouble is, the wave picture makes a clear, confident prediction about what controls the kick, and every part of it turns out wrong. So I'll let you make the prediction, because you'll make the one the wave picture makes, and we'll watch reality contradict you. Here's the knob. I can make the light brighter or dimmer. Brighter light, a more intense wave, carries more energy. What should that do to the electrons?
Easy. Brighter light is a bigger, more powerful wave, more energy pounding down on the surface, so it should kick the electrons out harder, send them flying off faster, with more punch behind them. Turn the light up, they come screaming out. Turn it down toward dim, they dribble out slow and feeble. Brightness sets the punch. Honestly, that one feels too obvious to be a trap.
That's the wave picture talking. Clean and confident and reasonable. And it is completely wrong. Turn the light brighter and the electrons do not come out with any more punch. Not a scrap. Every one of them leaves with precisely the energy it had before. Crank a dim light all the way up to blazing, searing bright, and every electron still comes off just as gently as when the light was faint.
Hang on, that can't be the whole story, because something has to change when I make it brighter. I'm pouring more energy in. It has to go somewhere. It can't just vanish. If the electrons don't come out any harder, then what does the brighter light actually do? Tell me it does something, because more energy in, no change out, sounds like it breaks a bigger law than the one we're fixing.
It does do something. It changes how many. Brighter light kicks out more electrons, a bigger crowd, but everyone leaves at the same gentle energy as before. More of them, never harder ones. A dim light frees a thin trickle, all at one speed. A bright light frees a whole flood, but the flood streams out at the trickle speed. Brightness sets the head count. It never touches the punch.
That is genuinely strange. So brightness, the one thing I was dead certain controlled the energy of the kick, turns out to only control the sheer number of kicks. Then what controls the energy? Something has to. If it isn't how bright the light is, then what's the other knob on this machine? Because I've plainly been reaching for the wrong dial this whole time.
The other knob is the color. The pitch of the light, the same ladder from the fire, red low, violet high. That alone sets how hard each electron gets kicked. Shine light just past the gate, and each electron crawls out feebly, however bright you make it. Shift up to blue, to violet, and each one comes tearing off with real energy. Change only the color, and the punch changes completely.
So I had the two knobs swapped the entire time. I was dead sure brightness set the energy, and color was mere decoration on top. And it's the exact reverse. Color sets the energy of each kick. Brightness only sets how many get kicked. Let me sit in how upside down that is, because the wave picture didn't gently nudge me wrong, it marched me wrong with total confidence.
It marches everyone the wrong way, which is why it's such a good miss to make out loud. And it gets sharper. There's a hard threshold sitting in the color. Below a certain pitch, down in the red, you can shine light on that metal as bright as you physically can, blinding, searing, for as long as you like, all day, and not one single electron comes off. Ever. Zero.
Nothing at all? However brutally bright you make it, for however long, genuinely nothing comes off.
Nothing at all, however brutally bright, however long you wait. And then you nudge the color past the threshold, up toward the blue, and even a faint, dim, feeble glow at that pitch starts freeing electrons the instant it lands. A whisper of blue beats a scream of red. That's the shape of the thing.
And that's the part that truly shatters the wave picture for me. With a wave, brightness is raw energy, so a blinding red light pours colossal energy onto that plate. If freeing an electron were only about pounding enough total energy in, that searing red should loosen something eventually. Instead, nothing, forever. But a dim blue whisper does it at once. So the total energy isn't what matters.
The total energy isn't what matters. The pitch is a gatekeeper, and below the gate no brightness buys you through. Look at what that does to the wave picture. A wave pours its energy in smoothly and cumulatively. So if you wait long enough, the surface should soak up enough to free an electron, whatever the color. The threshold says no, not ever. Something about this deal is not smooth and not cumulative.
It's all or nothing is what it is, and the color alone gets to decide whether you're even allowed into the game in the first place. Wait as long as you like below the gate, and you've nothing to show for it.
All or nothing. And the color is the doorman at the entrance. So who gets cornered into fixing this one? Same shape as before. A small, stubborn experiment, and somebody clever getting forced, against their better judgment, into an assumption they'd rather not make.
Let me guess, another reluctant patcher, holding their nose while they write it down. We seem to be collecting them tonight.
This one is Einstein, and here's the irony. He'd spent real effort elsewhere, proving light behaves like a wave. And now he's the one who has to say, when light lands on that metal, it arrives in lumps. Light comes in grains, packets, each carrying a definite energy set by its color. High-pitch, energetic packet. Low-pitch, feeble one. The same lumpiness Planck coughed up for the fire.
So Planck's lump, which Planck himself half hoped was only a bookkeeping quirk of hot glowing objects, Einstein takes completely at face value and says the light itself is genuinely built out of these lumps. All right, now let me see whether the lumps actually fix the metal plate. One lump comes sailing in, strikes the surface, and then what happens next?
One lump strikes one electron and hands over its whole energy in a single go. No dribbling. So whether that electron gets freed depends on how much a single lump carries, which depends on the color. Down in the red, each lump is too puny to free an electron, and it doesn't matter how many puny lumps you fire in, because each electron is only struck by one at a time.
Oh, so that's the threshold, in plain sight. A red lump is below the price of freedom, and because each electron only ever deals with one lump at a moment, a whole blizzard of red lumps changes nothing. Every deal fails, on its own terms. That's why blinding red does nothing. More and more failed transactions, not one big enough by itself to close.
Every deal fails, no matter how many you run. And above the threshold, each lump is finally big enough. One blue lump, one electron, one clean kick. And brightness falls into place too. A brighter light is more lumps per second. More lumps, more electrons freed. A bigger crowd, but each is freed by a single lump, so each leaves with an energy set by that one lump. What's left of it after paying the cost to break free? Head count from brightness, punch from color.
Let me say it back because this one rearranged the furniture in my head. Light comes in lumps. One lump kicks one electron. The color sets how big each lump is. So color sets the punch, and there's a threshold below which no lump is big enough, and piling on more doesn't help. And brightness is only how many lumps show up, so it sets the crowd size, never the punch.
That's the whole of it. And feel the size of what you've agreed to, because it reaches far past one metal plate. The field course convinced you, correctly, that light is a wave. It ripples, spreads, overlaps and interferes with itself. And this experiment tells you, just as correctly, that light arrives in countable lumps, one landing on one electron. Both true at the same time.
And, hang on, wait, Those two do not fit together. A wave is one continuous, spread-out thing. A hail of lumps is a great many separate little arrivals. A thing cannot be a single smooth ripple and a bag of discrete pieces at the same moment. Those two descriptions are at war with each other. So which is it really? What's genuinely flying across the gap from the lamp to the plate?
Don't try to resolve it. You can't yet, and neither could anyone alive at the time. It really is both, and the how of that is not a thing I can hand you tonight. It's the mystery this whole course circles. For now, take only the piece the experiment forces on us. Light comes in lumps, and the size of a lump rides on its color.
And I am firmly not to picture the lump as a tiny little ball. You keep steering me off that, and I can feel why, but say it plainly.
Resist that picture with everything you've got. It is not a little pellet, not a bullet, not a grain of sand, just light and energy arriving in countable grains. The moment you reify it into a solid pebble flying through the air, you've told yourself a comforting lie, and it'll walk you off a cliff a few episodes from now. Leave it a lump, and leave the lump mysterious.
I'll keep my hands off the pebble, though lump makes me want to picture one, and you've forbidden the very thing the word suggests. Fine. But two witnesses now, both saying the same odd word, grains. Energy in grains, from the fire. Light in grains, from the metal. I can feel a pattern lifting off the page, but you promised a third, and said it cut closest to the bone.
The third, and the one that, by every right, should never have let either of us exist to sit here and talk about it. The first two cracks bruised the old physics. This third one goes for the throat.
That's a big claim to make. So set it up the same way you did the others. Give me the innocent, comfortable picture first, before you take a hammer to it.
Same move. We start from the most innocent picture the clock and the field politely hand you, and we follow it honestly, step by step, until it detonates. Picture an atom. When I say the word atom, what's the picture that rises up in your mind's eye, unbidden?
The one off every school poster and half the company logos, a little solar system. A heavy something in the middle, the nucleus, and tiny electrons whizzing around it in orbits, like planets round a sun. The clock course made me comfortable with orbits, a central pull, a thing circling it. Same as a planet held by gravity, only with electric pull. That picture feels completely safe.
It feels safe because you built it from two things you trust: the clock's orbits and the field's electric pull. A positive nucleus tugs a negative electron, and it falls around it in a circle, the way a planet falls around its star. And now I bring the other half of the field course back in, and it kills the picture in a heartbeat. What does an electric charge do the moment it accelerates?
When a charge accelerates it, oh no, it radiates. The field course was blunt about that one. A charge that's speeding up or slowing down or changing its direction throws off light. It sheds energy as radiation. That's the whole trick behind making a radio wave, isn't it? You shake charges up and down an aerial, and they broadcast out into the world. A jiggling charge sends out a signal.
A jiggling charge broadcasts. Now look hard at your safe little orbit. An electron running around a circle is changing direction at every instant. We nailed this in the clock course. Going round a circle is acceleration, constant turning, even when the speed never changes. So the orbiting electron is an accelerating charge without pause. And by the field's own iron rule, it must radiate the entire time it orbits.
And if it's pouring out energy the whole time it's going round, energy it doesn't have a bottomless supply of, then it's steadily losing it. It can't keep sailing round the same orbit while it bleeds energy away like that, so it must be falling inward, sinking closer and closer to the nucleus as it drains itself dry.
Spiraling inward. It bleeds energy, drops toward the nucleus, whips around faster, radiates harder, drains quicker, drops further still, a runaway spiral feeding on itself tighter and tighter. And when you put real numbers to the collapse, which I won't, but they did, the electron goes from an ordinary orbit to crashed into the nucleus in less time than it takes to say the word collapse.
So the clock and the field together, taken at their word, say every atom should instantly wind down and crash. Which means, let me follow this to the bitter end, no stable atoms. None. Anywhere. Ever. Everything made of atoms should have slumped into a dead heap of wreckage in the first instant of existence. Including, I can't help noticing, everything I'm made of.
Everything. You, the chair you're sitting in, the air between us, the star overhead, all of it built from atoms that, by the best physics of 1900, cannot survive a single heartbeat. The theory doesn't predict a wobbly atom or a short-lived one. It predicts no lasting matter at all, a whole universe that snuffs itself out before the first second is done.
And yet here we both very plainly sit, having this conversation, not snuffed out, not a dead heap, stubbornly, inconveniently existing.
Made entirely, head to toe, of the atoms that were supposedly forbidden from lasting an instant. Every atom in your body is a standing refutation of the best theory anyone had. That's the third crack, the one that goes for the throat.
The first two cracks were about getting a curve wrong, or a kick wrong. Bad, but survivable. This one is about whether anything is even allowed to exist. The clock and the field don't fumble a detail, they forbid the entire world, us included. That's not a decimal you can tidy. So the atom obviously does not collapse. I'm talking, so that's settled. What does it do instead?
It does a second thing the collapse picture can't explain either. And here's the beautiful part. The two mysteries turn out to be one, wearing two hats. Feed an atom some energy, heat it or run a spark through a gas of it, and it glows. But watch how. Not a smooth rainbow. A handful of sharp, separate colors. A few precise lines of pure color with plain black darkness between.
Separate lines? You mean, if I take that glow and spread it out the way a prism spreads sunlight into a full rainbow, I don't get a smooth, continuous band of color. I get a few bright, narrow stripes sitting at their own particular colors, and then nothing whatsoever in the gaps between them. Only stripes and darkness.
A few bright stripes, each at its own exact color, with black gaps between, like a barcode painted in light. And here's the haunting part. Each kind of atom has its own barcode, always the same, sharp and repeatable. One element gives you this precise set of lines and no others every time, anywhere in the universe you look. It's a fingerprint, a signature written in color.
But the little solar system atom, the comfortable picture I walked in with, has no idea why. It can't explain that barcode at all, can it?
No idea at all, not the faintest. A planet can orbit at any distance you please. Nudge it a little closer or further, and it settles into a slightly different orbit. So a smooth atom ought to smear out a smooth, continuous band of color, every shade blending into its neighbor. It has no business producing a strict little barcode of separate lines. And yet a barcode is what nature hands you.
Right. If the electron can spiral inward through every distance on the way down, it ought to sweep through every color along the way, and I'd see one continuous smear. Instead, I get a few sharp lines and hard, ringing silence in between, as though only certain colors are permitted. Which sounds, now that I hear myself say it, like the lump business again. Certain amounts allowed, everything in between forbidden.
And here's the man who wrote it down. Bohr. He looked at the impossible collapse and the strict barcode side by side, and made a bold, unjustified leap, as reluctant as Planck's coin. He said, the electron may not orbit at any distance. Only certain orbits are allowed, a fixed set of rungs, and between them, Nothing.
So he simply forbids the in-between. By royal decree, more or less. The electron can sit on this rung or that rung, but never in the gap between them, and never spiraling smoothly down through it. And that, I'm guessing, is how he halts the collapse. If there's a lowest allowed rung, the electron settles onto it and runs out of anywhere lower to fall to?
Precisely. There's a lowest rung, a smallest allowed orbit, and once the electron's on it, there's no permitted orbit beneath to spiral into. The staircase has a bottom step, so the electron parks there and stays, not radiating, and the atom is stable at last. Not because the field's rule was wrong, but because the electron is forbidden from taking the smooth downward path that rule assumed.
No in-between, so no spiral, so no collapse. That's clean. And the barcode, those sharp separate lines, those have to come straight from the rungs as well, don't they? Because if the electron can only ever sit on certain particular rungs, then when it moves between them, it can't move by any old amount. Let me try to finish this one myself before you do. I think I've got it.
Go on and finish it yourself.
When the electron jumps from a higher rung to a lower one, it sheds the energy difference between them. Not a bit more, not a bit less. And it sheds it as a single lump of light. One jump, one lump, one exact colour, because the colour rides on the lump's energy. Fixed rungs make fixed gaps, make fixed colours. The barcode is the staircase, read out in light.
The barcode is the staircase read out in light. That's it. And notice, one idea has done two separate jobs at once. It gives the atom a bottom step to rest on, so it never collapses, and it gives the jumps fixed sizes, so the glow comes out a sharp barcode instead of a smear. Both from the single assumption that the orbits are grainy, that only certain ones are allowed.
And that's the third time tonight now that we've watched this same rescue come walking through the door. It's getting hard to call it a coincidence.
The third time, and no, it isn't a coincidence. It's the whole point. Let me line all three up. Planck, energy only ever handed over in lumps. Einstein, light only ever arriving in lumps. Bohr, the orbits themselves only in a grainy set of allowed rungs. 3 different experiments, 3 reluctant people, and one strange word dragged out of every one of them against their will.
A fire, a metal plate, and a single atom. 3 of the dullest, most ordinary things in the world, and all 3 saying the same impossible thing.
A fire, a metal plate, and a single atom, and the same word forced out of each. And now you should be the one to pull all 3 together into the single thing they've been circling all night, because you can feel them wanting to become one statement. So go on, say what the 3 lumps are really telling us.
Okay, the fire says energy comes in lumps, the metal says light comes in lumps, the atom says even the orbits come in lumps, only certain ones allowed, the rest forbidden. 3 humble experiments, 3 grains. And what all 3 are telling me, in the same quiet voice, is that the world is not smooth. Down at the very bottom, something is telling me the world is.
Say it. Go on. You've earned the whole sentence, every word of it.
The world is grainy. That's the whole thing. Underneath the smooth clock and the smooth field, right down at the smallest scale, everything comes in grains. Energy, light, the orbits an electron is allowed to hold. None of it flows smoothly the way the big world looks like it does. It's all counted out. The smoothness we built 2 centuries of physics on is a story the bigness tells us.
The thing every one of the founders was dragged bodily toward, one clenched, unwilling step at a time, not a single one of them wanting to go. Nature is grainy at the bottom, and once you've seen it in all 3, you can't stop seeing it. But it raises a question that ought to be bothering you already.
It is bothering me, badly. Nobody noticed this for 200 solid years. How? If the world is really and truly made of pixels all the way down, then how on earth did the clock look so utterly flawless for 2 whole centuries, of the most careful work imaginable.
Because the grain is fantastically, absurdly small. That's the last piece, and the one that makes the whole unbearable thing bearable. There's a brand new number that sets its size, a new constant of nature, Planck's, that no physics before had ever needed. And it's so vanishingly tiny that for anything you can see, hold or throw, a smooth pour and a heap of grains are impossible to tell apart.
Small enough that the graininess never once shows its face in ordinary life, because I have genuinely never caught the world being made of pixels, not for a moment. Water pours out smooth as silt, the light from a lamp seems perfectly smooth. A thrown ball carves a smooth, clean arc through the air. Nothing I handle looks the least bit grainy.
A poured stream of water looks smooth, for the same reason a beach looks smooth from the top of a distant cliff top. The grains are far too small to catch from up there. So the clock looked flawless for 200 years, not because the world is actually smooth, but because we were always working so enormously far above the grain that we couldn't possibly feel it under our feet.
So Newton and Maxwell weren't wrong about the great big smooth world at all. That's what I need to get straight. They were only ever wrong to assume it went all the way down, right to the bottom without a break. They simply were never looking small enough to bump into the pixels. The old physics wasn't a mistake. It was a view from very high up.
That's why the old physics keeps its power. Zoom back out to planets and cannonballs and radio waves, and the grain washes out. The clock and the field are as flawless as ever. It's only when you climb down, to the fire's tiniest jigglers, to single electrons, to one atom, that the grain swells into the whole story and the smooth picture shatters.
Same world then, seen at two completely different scales. And a brand new number quietly marking the border between the two. Above it, the smooth clockwork you can trust with your life. Below it, the grainy strangeness. And that number is the fence line running between them.
Worth carrying out the door, that image. And here's the strangest thing about that number. It is small, but it is emphatically not 0.
And that's the whole hinge, isn't it? That tiny number does an enormous amount of quiet work. It's the exchange rate between the smooth world I live in and the grainy one underneath. Set it to 0 and the grains vanish, and hand back the good old smooth clockwork. But it isn't 0. And that thin gap is where an entire hidden world has been living.
That gap is the whole enormous subject you're about to spend a full course living inside. And before we go on, I want to be straight about what we have, and have not, done here tonight.
Go on then, be square with me. Because part of me right now wants to plant a flag and declare a great victory. 3 cracks, 1 word, grainy. The whole world explained. Roll the closing credits, everybody home. But the look on your face is telling me it is not remotely that tidy. So tell me plainly, what am I not allowed to believe yet?
You're not allowed to believe we've explained a single thing. We've named the crisis, not resolved it. 3 experiments broke the old world open, and 3 reluctant people wrote patches that make the numbers come out right. But a patch that works is not an understanding. Planck couldn't say why energy comes in coins. He only found that it must. Einstein couldn't say how light is a wave and a hail of lumps at once. We ran into that wall tonight, and I told you to leave it standing. And Bohr could not say why only certain orbits are allowed. Everyone nailed the what and stayed blank on the why.
So the patches are less a finished house and more 3 signposts hammered into an empty field, each reading something real is buried here, with nobody yet able to dig any of it up. What a lump of light truly is. How light can be a wave and a grain at once. Why an electron is allowed only some orbits. None of those are answered. Those 3 are the homework.
Those 3 are the whole course. The long, patient digging underneath the signposts, building the machinery that says what a lump genuinely is and how a thing can be wave and grain together without tearing in half. And here's the part to carry out the door. These three fixes worked perfectly, gave right answer after right answer, and were understood by precisely nobody, not even the people who wrote them. That working but not understood discomfort is not a flaw in the story. It's the doorway itself.
And that matters to me, because the quantum gets dressed up in an astonishing amount of nonsense. None of this came from mysticism or a grand vision of oneness. It came from a fireplace that refused to be a death ray, a plate that refused to obey brightness, and an atom that refused to collapse. Hard, dull, immovable facts. The strangeness was forced on physics from outside, against its wish.
Nobody chose the quantum for being beautiful, or mysterious, or profound. Every one of the founders was a conservative, dragged against their own taste, because a stubborn experiment left no room to refuse. It is the soberest revolution there has ever been, cornered into existence by three plain experiments, not dreamed up in a reverie. The wonder is real, but it comes after the arithmetic, never instead of it.
So where it leaves me tonight is, I walked in thinking physics was nearly a finished portrait, with a few smudges to wipe, and I'm walking out with 3 clean holes punched through the canvas, and one word, grainy, showing through them. Not a theory, a crisis, and a clue. The clock has cracked. There's a whole strange world on the far side, and we're only at the door of it.
The right place to end, standing in the cold draft coming through the cracks. The old smooth world isn't wrong, so much as it is the far-off view of a world that, up close, is counted out in grains. Everything from here is learning the rules of that grainy world. Rules that look nothing like the clock, stranger than any patch we scribbled down tonight.
Then, before we stop, give me the very edge of the next one, because I can tell you're already quietly resting a hand on a door handle. If tonight was 3 separate experiments, all saying the world is grainy, what is the single experiment that comes next? What are we walking into?
The strangest of the whole lot. It takes the wave and grain puzzle we left standing tonight and makes it 1,000 times worse, right in front of your open eyes. You take the tiniest pieces of the world and send them, one at a time, one lonely piece after another, at a barrier with 2 narrow slits cut into it. And you watch where each one lands on the far side.
One at a time, so there's no crowd, nothing bumping into anything else. A single little piece, then a long wait, then the next, and so on down the line. I'd expect them to pile up in 2 plain heaps, one behind each slit, go through a slit, land behind that slit. That's the obvious thing, surely. What else could a single lonely piece possibly do?
What else, indeed? But that is flatly not what they do. Sent one at a time, with nothing to interfere with, the lonely pieces slowly build up the exact striped pattern you only get from a wave passing through both slits at once and rippling into itself, as though each indivisible piece had gone through both slits at the same time and interfered with itself on the way.
Each single one going through both slits at once? No. No, that breaks the very last solid thing I had left standing in my hands, which was that a lump is at the very least somewhere. It's in one single place. You're smiling at me again, which I very quickly learned means you are absolutely not going to rescue me from that one tonight either, are you?
Not tonight. Tonight was only the cracks, the proof the old smooth world cannot hold, and your first clear sight of the grain underneath. Next time we walk through those 2 slits together and watch a single grain refuse point blank to be in one place, where the true strangeness and the real theory finally begins. Sit with the graininess until then. Let it stay as odd as it is.
I will, and honestly, I couldn't put it down now if I tried. So that's tonight. By 1900, we thought we were polishing the last decimals, and instead, a fire, a plate, and 1 atom told us the world is secretly made of grains, and nobody knew why. The clock has cracked. Next time, the mystery at the heart of it all. 1 piece, 2 slits, both at once. We'll meet you at the door.